Hello. So derivatives are limits of difference quotients, but taking the limit of a difference quotient every time we want a derivative would get very tedious very quickly. So in this video, we present some differentiation rules that let us take some derivatives without messing around with the limits. The first rule, I hope, makes intuitive sense if we remember that the derivative is a rate of change. What is the derivative of a constant? Well, it's kind of right there in the name. Constant functions are constant. They don't change. So the rate that a constant function is changing at is zero. And there is our very first rule. So the derivative of the constant function 5 is 0. Now, n has served me well, but I think it's time to move on. And then a less intuitive rule, the power rule, which tells you how to take the derivative of x raised to a power. And you're not going to guess this one, unlike the constant rule, which is very intuitive. But the derivative of x raised to a power is the power times x raised to the power minus 1. So, for example, the derivative of x to the 7th, the power comes down, 7x, and then the power is reduced by 1, so 7x to the 6th power. The derivative of x raised to the 1/3 power. The fact that we have a fraction up here doesn't change anything. The power comes down, 1/3 x, and then we subtract 1 from the power. We reduce the power by 1. 1/3 x to the -2 thirds. A few special cases of this. This is actually is sort of a special case because fractional powers of this form, 1 divided by n, are roots. That is the derivative of the cubed root We can take this using the power rule, because the cubed root is precisely this. It's precisely the 1/3 power. And we already did this. 1/3 x to the negative 2/3 power. The derivative of the square root. Well, the square root is the 1/2 power. And once we've made that connection, this is a completely straightforward application of the power rule. The 1/2 comes down. We subtract 1 in the exponent. 1/2 x to the negative 1/2. Although this is often written differently, algebra simplification time. A negative exponent is the same as a positive exponent in the denominator of a fraction. So x to the negative 1/2 is 1 over x to the positive 1/2. What's x to the positive 1/2 again? That's just another way of writing the square root. So this is 1 over 2 times the square root of x. This trick, by the way, also lets us differentiate something like 1 over x. If you can remember that 1 over x is x to the negative 1 power, the power rule just works. The power rule always works. The fact that we have a negative number up here doesn't do anything. The power comes down. We subtract 1 up here. Negative x to the negative 2nd, which we could then write as negative 1 over x squared. So in an applied calculus course, the power rule is kind of our main rule, because we don't work with the trigonometric functions. So in our regular calculus sequence, we'd have 6 trig functions and 6 other derivatives. Here we only have a small number of functions we're going to work with, and the power rule is really the big one. We'll learn the derivative of the powers, or rather we just did learn the derivative of powers, and then exponential functions and logarithmic functions later in the course. And I think these might be the only derivatives that we learn in applied calculus. Now, a few more rules, though, not the end of the video. So we know how to take the derivative of x to the fifth now. It's 5x to the fourth. What about the derivative of 7x to the fifth? It turns out that we can take this derivative without a lot of fuss. The fact that we have a 7 here doesn't change things too badly. The derivative of a constant times a function is the constant times the derivative of the function. Mixing my notation here. But, going back, what this is saying is that the constant just sort of sits there. And you take the derivative of the function. So we get 7 times the derivative of x to the fifth is 5x to the fourth. 35x to the fourth. All right, what about x squared plus x to the fifth? We can take the derivative of x squared. We can take the derivative of x to the fifth. Can we handle the derivative of their sum? The answer to this question is yes. The derivative of a function plus or minus another function is just the sum or the difference of the derivatives. So here the derivative of x squared is 2x, and the derivative of x to the fifth is 5x to the fourth, and we just add those together. A few parting remarks. First, we've seen that the derivative of addition and the derivative of subtraction is a very sort of what you might expect. If you want the derivative of a sum, you take the sum of the derivatives. If you want the derivative of a difference, you take the difference of the derivatives. Sadly, this does not hold for multiplication or division. We're going to have to learn kind of complicated rules for multiplication and division. The other warning I want to leave you with is that this power rule works for x raised to a power. If instead of x raised to a power, what if we have something more complicated? 1 plus x squared raised to the 10th. The power rule does not work here. We need more complicated machinery. That is to say, this derivative is not 10 times this quantity raised to the 9th. We need other tools here. So this power rule works for x raised to the n. It does not work for more complicated expressions raised to the n. And with that, we learn quite a bit of material in this section, and I will leave you to digest that.